we compare the relative reducing strengths of a bunch of different reducers. And if you can write the equation for the half reaction, which shows what the reducer is oxidized to, then you can make a list of half reactions. And after you have observed the relative reducing power of the various reducers whose strengths have been compared, you can make the table. So with that, we got these two half reactions last time. Now, in addition to developing these two half reactions and starting this table, which we're going to construct, a short table in that it'll only contain 6 half reactions, we also talked about the reactions which you would do, the investigations which you would make to be able to decide on the relative reducing strengths of different reducers. For this case, we found out that sodium reduced water. And we mentioned that as long as there is sodium in contact with water, this system will never come to equilibrium. Upshot, sodium is a much stronger reducer than the hydrogen hydroxide ion combo. Now, along with this, we took a peek at the stuff that you folks did in 45 laboratory last term in Assignment 5, Part 1, Fundamental Aspects of Redox Reactions. Along with that, we talked about what you would have to do if you were going to make an electrochemical cell which would be capable of delivering usable electrical energy from zinc, hydrated zinc ion, copper, hydrated copper ion. Reducer, reducer, conjugate oxidizer of this reducer, conjugate oxidizer of this reducer. Investigations are simple. You put this reducer in contact with this conjugate oxidizer and this reducer in contact with this conjugate oxidizer. Because either this reducer is stronger than this reducer or this reducer is stronger than this reducer. They're different materials, they must have different reducing strengths. What do we find out? This reducer immediately reduces this oxidizer to this as a reduction product. While this reducer, in reducing this oxidizer, this reducer oxidizes this stuff. Correspondingly, this reducer in contact with this oxidizer gives no reaction. So we know this reducer is a stronger reducer than this reducer. That's as far as we got with this last time. Now, the problem is, if you have, which is what we did last time, a solution containing copper ion, the oxidizer which is capable of oxidizing this reducer, and you establish direct contact between the reducer zinc and the oxidizer hydrated copper ion. Do electrons flow? You betcha. But they flow directly from the reducer to the oxidizer, and you have what the electrochemists call a short circuit. That system, as it stands, cannot be used to deliver usable electrical energy. What you have to do is to construct a system which will require the electrons, as they flow from zinc atoms in the zinc strip, creating zinc plus 2 oxidation state. You've got to make those electrons flow through an external circuit. And that's how you get usable electrical energy before those electrons get to the stuff they reduce. So back to demonstration. Here, beaker with hydrated copper ion. Here, beaker with hydrated zinc ion. Now last time we found if I put the copper strip in the hydrated zinc ion, nothing. If I put the zinc strip in the hydrated copper ion, reaction. But that's the short circuit. So notice what I have so far done. The system which contains the oxidizer, hydrated copper ion, is in this beaker. And the system which contains the reducer, the zinc strip, is in this beaker. And I have connected a copper strip, which is immersed into the copper ion solution, to a wire. The wire in this case goes to a voltmeter. And another wire goes from the voltmeter to the zinc strip. This way, we have the oxidizer physically separated from the reducer. Oxidizer, again, is hydrated copper ion. Reducer, zinc. So if I can get electrons to flow from the zinc as it gets oxidized to zinc ion, and make those electrons flow through this meter, then I will be able to use the electrons as they flow from the zinc, travel through the system to get to the copper ion as a consequence of passing through the copper strip, which in this case is simply functioning as an electron carrier, a conductor. But as things stand, if the electrons were to flow this way and get to the copper ion, how could they get back to this system and complete the circuit? As things stand, they can't. So we're going to use a gizmo to allow us to complete the circuit. And in this case, get a volt reading. Here's such a gizmo called a salt bridge. You can see pictures of this. Well, I don't know that I have any pictures of this in the notes, but if you look in a textbook or online, you can see all kinds of pictures of fancy salt bridges. Now when I put one end of the salt bridge in the zinc ion beaker and the other end of the salt bridge in the copper ion beaker, now I've got a complete circuit. And if you take a look, which I believe you did yesterday in discussion class, at the electrochemical potential for oxidizing zinc to zinc ion. Look at table 2. Plus 2 electrons. What do you see as the E0 value for this half reaction? You see this? You're looking at the half reaction where zinc, in the presence of water liquid, oxidizes to hydrated zinc ion with the liberation of 2 moles of electricity per mole of hydrated zinc ion produced at a standard electrochemical potential of plus 0.763 volts. You see that? And for copper ion, hydrated, collecting electrons to become copper strip or copper metal, and putting the water molecules back in the solution, you see an E0 value of how much? What do you see? Here's the value you see. Plus or minus? Plus or minus? As you see it in the table in the notes, you're looking at copper reacting with water to become this, liberating electrons. Potential for that is minus 0.34 volts, correct? But we're looking at this in the opposite direction. We're talking about the coupling process. This is the half reaction whose directionality has been reversed relative to what you see in the notes. That means in this direction, E0 is 0.34 volts. Add them up, 1.10 volts. Let's say what we got with our meter. Well, those of you up close, can you see it? Read it. 1.09, that's not bad. We're pretty close. And that is an illustration of how you make an electrochemical cell which can be used to deliver electrical energy, and how for this particular cell we can observe the E0 values that would follow from the information that you see in Table 2. Now, another comment that I will make is to make a battery, which is usually a collection of electrochemical cells hooked up in series, like your car battery. How many cells in your car battery? Do you have a car battery? Yes. You have a car? How many cells? In the lead storage battery, how many cells? Don't know? 6. There's 6 lead cells in the lead automobile storage battery, hooked up in series. And when we get further into the analysis of half reactions, we'll see that the standard operating potential for a lead cell, the likes of which you have in a car battery, is about 2 volts. What voltage does your car battery operate at? 12 volts. Does that correspond to the 6 cells hooked up in series? 6 times 2 is 12. How about that? All right. Now we're done with this, so let me disassemble this. You will not find salt bridges in your car battery or other operating batteries because the resistance of salt bridge is very great. The salt bridge business is used, practically speaking, only for demonstrational purposes to show you how we can read E0 values, the likes of which we've just done. Now, let's go back to the half reaction table and proceed with further development. Here's what we have so far. Strength as reducers increase from bottom to top. Sodium is a stronger reducer than hydrogen hydroxide ion. And strength as oxidizers increase from top to bottom. Now, experiments. Experiments we so far have done is sodium and water. Zinc with water and copper and water. From a practical standpoint, what do you think is going to occur if we put a zinc strip in water liquid or a copper strip in water liquid? You ever thrown pennies into a fountain? Have you seen pennies thrown in the fountains? Have you jumped in the fountain to scrape up the pennies? Why not? Of course, the park keepers might not be happy with you if you do that. Do you think copper has a natural tendency to react with water and become oxidized? Do you see these pennies which have been thrown in the fountains react vigorously with the water? No. How about zinc? Now, if you use the information correctly that's in our half reaction table, table 2, you'll see that zinc does in fact reduce water. But the reaction, practically speaking, doesn't go anyplace, because as soon as zinc reacts with water, you form on the surface of zinc, a coat of zinc hydroxide, and that stops the reaction. So practically, zinc doesn't react with water. So with that, we can recognize that zinc is a weaker reducer than sodium, as well as copper, because we found that sodium reduces water quite vigorously. Now, what do we know about zinc versus copper? We just found out that zinc is a stronger reducer than copper. So, we'll take the liberty of adding this half reaction. The half reaction involving the oxidation of zinc, the hydrated zinc ion, and put it in the table as reaction number 3. If practically zinc doesn't reduce water, which we could demonstrate by just putting a piece of zinc in water and see nothing take place, that's telling us the hydrogen hydroxide ion combo is a stronger reducer than zinc, which means the hydrogen hydroxide ion combo can reduce or is expected to reduce hydrated zinc ion, whereas zinc does not reduce water. Now, let's take some of this stuff. 1 molar sulfuric acid. These will be the next experiments. Zinc in 1 molar sulfuric, and copper in 1 molar sulfuric. I'm not even going to bother putting the copper strip in the 1 molar sulfuric because it leads to no reaction, and students have a habit of getting bored when no reactions occur. So do instructors. But I will construct the system. Some 1 molar sulfuric and zinc. There again is the reagent bottle with its label. Now we need some observations. Look carefully into the beaker. Do you see evidence of a reaction?
Yes.
Louder. They can't hear you.
Yes.
What is the evidence which you see?
It's bubbling.
It is bubbling. I don't know what it is.
Zinc.
Zinc is bubbling. I don't see the zinc bubbling here.
It's bubbling where there's H2SO4.
The bubbling is occurring where the zinc is in contact with the solution. We agree with that?
Mm.
You folks concur? Bubbling. Well, if bubbles are being liberated, what does that indicate is being produced?
Gas.
Gas. Gas is being produced. Okay. Now, if I allow this system to stand, the zinc will continue to be consumed because in this system, zinc is being oxidized to hydrated zinc ion. And we know, in this case, the oxidation is being done by 1 or more of the component species of sulfuric acid solution. What do you think we should do now to try to determine what the stuff is in sulfuric acid solution that's doing the oxidizing? Inventory. Good. Have you done it? Let's do it. Have we written this inventory? Do you recall from our analysis of sulfuric acid solution that at a molarity of 1, the hydrogen sulfate ion molarity will be much greater than the sulfate ion molarity. So we'll not put sulfate ion in our inventory. Which species from this inventory can we strike immediately because it's not the oxidizer of zinc? Zinc water is a no-go. Just like copper water. Now we got to make a decision. Do you think it's hydronium ion or hydrogen sulfate ion which is principally responsible for this oxidation process? Why do you pick hydronium ion? Well, all right, tell me more. Well, tell me why. Based on observations, can you make this conclusion? Why is it fair? Well, let's talk a little bit further about this system and consider the fact that for this system right here, gas is produced along with this. What do you think the gas is? How about these as possibilities? From water I can get oxygen, from water I can get hydrogen, from water I can get ozone. These are all gases produced from water. I mean from hydronium ion, pardon me, to say water. I meant hydronium ion because of the component elements of hydronium ion. From this, along with these gases, I could make these gases. Now tell me, in the hydrogen sulfate ion, what's the oxidation state of sulfur? What would you do to find out? Lewis structure, partial electron. What's the oxidation state of sulfur in this stuff? Now, if I provide you with the reminder, because we can do Lewis structure analysis, of course, which is the way to do it if you didn't know, but in all compounds of oxygen, compounds which contain oxygen, except for peroxides and superoxides, oxygen is always in what oxidation state? -2. Oh, and there's one other stuff. Oxygen difluoride, which is the only material that contains oxygen in a positive oxidation state. Well, those are hardly oxygen difluoride. Well, if oxygen is a -2 oxidation state, what's the oxidation state of sulfur in SO3? +6. And if you analyze this, you'll find the oxidation state of sulfur is +6. So is this a possible reduction product? Is it possible to reduce this and get this? That's the question. The answer is no. Why not? Sulfur +6, sulfur +6. No redox. Now, of course, the most direct and best way by far to find out what the gas product is as it is liberated by the reaction, we catch it and analyze it. And if we catch it and analyze it, what do you think we're going to find this gas to be? Any bets? Well, let's go back to some of the stuff we mentioned the other day. By reducing this or this, could we make this? By reducing this or this, could we make this? Could we make this? What's the oxidation state of oxygen in this stuff? Oxidation state of oxygen in this stuff. In this stuff. -2. Oxidation state of oxygen? I can't make these by reducing these. So, it's this or this. Want to make a bet what it is? Well, let's first tell you what it is, and then talk about why it's reasonable to conclude that that's what it is. Here's the stuff. Okay? If we caught this gas and analyzed it, we find out that it is hydrogen. Now then, tell me. Zinc is not reducing water to make hydrogen, whereas we found zinc now to readily reduce hydronium ion to make hydrogen. Now, of course, hydrogen sulfate ion is also reducible to make hydrogen because these are each sources of H atoms, right? Which of these is the better source of reducible H atoms? Which of these is the better source of reducible H atoms? What do I mean by a reducible H atom? If I have a reducible H atom, what oxidation state is shown by H? What's the oxidation state for H in water? Sodium reduced water. Oxidation state of H in water is +1. So reducible hydrogen is +1 hydrogen. Hydronium ion or hydrogen sulfate ion. Which of these is the better source of reducible hydrogen or +1 hydrogen? Hydronium ion, why? Because? Is it a stronger acid? Back to acid-base chemistry. Did you, in talking about the rules of the road for developing half reactions, which is what you did yesterday in discussion class, come to realize that many of the rules of the road depend on acid-base chemistry? Well, if you didn't, you will now. So once again, we're looking at the situation where you got to know the acid-base chemistry to get on successfully with this. And if you look at the half